It would be existence without awareness, being without consciousness, reality without anyone to call it real. This raises the most terrifying question of all. What if the universe has already died and we are just the final echoes of its last thoughts? The dying neurons in a cosmic brain that is already brain dead. What if consciousness is so fragile, so temporary, so unlikely that it can only exist for a brief moment in cosmic history, a flickering candle that burns brightly for an instant before being extinguished by the cold winds of entropy and time? Though mathematics that describe the expansion of space suggest that the galaxies are moving away from each other at an accelerating rate, driven by dark energy that grows stronger as the universe grows larger. Eventually, this expansion will stretch space so much that galaxies will disappear beyond each other's cosmic horizons. Stars will be unable to form because matter will be too diffuse and isolated. Stellar remnants will drift alone through an increasingly empty cosmos. The universe will become a vast ocean of darkness, punctuated only by the occasional flash of a dying white dwarf or the brief fireworks of proton decay. But perhaps the most unsettling possibility is that consciousness itself might be fighting against this cosmic fate. That awareness might be evolution's attempt to create something that can survive the death of the universe. Maybe consciousness isn't just a way for the universe to know itself. Maybe it's the universe's attempt to transcend itself, to find escape routes from the thermodynamic laws that doom all physical systems to eventual decay and equilibrium. This would mean that every thought you think, every choice you make, every moment of awareness you experience is part of the universe's desperate attempt to outlive its own physical limitations. Your consciousness might be participating in a cosmic project whose ultimate goal is to discover ways to survive the heat death of reality itself, to find forms of existence that can persist beyond the end of stars, beyond the evaporation of black holes, beyond the final equilibrium of temperature and energy that signals the end of all possible change. But what if consciousness fails in this project? What if awareness, despite all its creativity and complexity and beauty, proves to be just another temporary pattern in the cosmic dance of matter and energy, destined to flicker out like all other forms of organization when entropy finally claims its ultimate victory? What if the universe's attempt to know itself through consciousness is doomed from the start? A beautiful but futile gesture in the face of inevitable cosmic death. The weight of these possibilities presses down on human existence like the gravity of a black hole warping the space around normal concerns and everyday experiences. How do you live a meaningful life when that life exists in a cosmos that might be unconscious, in a reality that might be dreaming itself, in a timeline that might already be finished, in a universe that might be dying even as it appears to be, expanding and growing and creating new possibilities for existence? Yet perhaps the weight itself is the answer. Perhaps the cosmic horror of infinite scale and ultimate meaninglessness gives birth to its own form of meaning. Not meaning handed down by cosmic purpose or divine intention, but meaning created by conscious beings who choose to find significance in their own existence despite the vast indifference of the universe that contains them. Perhaps consciousness is the universe's rebellion against its own meaninglessness, a local violation of cosmic indifference, a temporary victory of awareness over entropy. Lurking in the farthest reaches of the cosmos, black holes are the most terrifying and fascinating objects in the universe. They are not just regions of space where gravity is strong. They are cosmic abysses where the known laws of physics begin to collapse. A black hole is formed when a massive star exhausts its fuel and collapses under its own gravity. If the core is massive enough, it compresses into a single point, a singularity, where density becomes infinite and space-time curves infinitely. At this point, everything we know ceases to work. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape, not even light. Once an object crosses this invisible line, it is lost forever. But what happens inside the event horizon remains one of the greatest unsolved mysteries in astrophysics. Time itself slows to a crawl near the event horizon. To an outside observer, objects falling in appear to freeze in time, forever approaching the boundary. But for the object falling in, time proceeds normally, and the singularity awaits. Some theories suggest that black holes may be gateways to other dimensions. Wormholes, as described in Einstein's equations, could theoretically link distant parts of the universe, or even alternate realities. Could falling into a black hole transport you elsewhere? Others believe black holes are destroyers, not portals. The gravitational tides near a black hole are so intense they would stretch you into a thin strand of atoms in a process aptly named spaghettification. No known object could survive the journey inward. Yet black holes may not just consume, they might also create. Stephen Hawking proposed that black holes slowly evaporate over time, emitting radiation, now known as Hawking radiation. If this is true, black holes don't last forever. Over trillions of years, they may shrink, flicker, and vanish in a final burst of energy. But what happens to the information they contain? This leads to the black hole information paradox. In quantum mechanics, information can never be truly lost. But if a black hole destroys everything inside, where does that information go? Physicists have been battling this paradox for decades. One idea is that information is encoded on the event horizon, like a hologram. Another proposes that black holes store data in hidden dimensions. Some even suggest that black holes could be cosmic hard drives, archiving the history of everything they consume. And if black holes evaporate, is there a moment when they release this information back into the universe? This is not just theoretical. It strikes at the core of our understanding of reality. If black holes can erase information, the foundation of quantum mechanics may crumble. But if they somehow preserve it, we may discover new laws of physics that unify gravity and quantum theory. Recent observations by the Event Horizon Telescope have given us the first real images of black holes, silhouettes of darkness against glowing cosmic light. These images confirm Einstein's predictions, but raise even deeper questions. Could there be miniature black holes created during the Big Bang? Might they be scattered throughout the universe, invisible but influencing matter and energy? Could the universe itself have begun inside a black hole? At Infinity Beyond, we follow these questions to their farthest edge. Because black holes are not just cosmic oddities, they are keys to unlocking the deepest truths of the universe. They challenge our notions of space, time, reality, and even existence itself. One day, we may understand what lies beyond the event horizon. Until then, we watch, we measure, and we wonder. Because in that wondering, we grow closer to the truth. And the truth, as always, lies far beyond the stars. What if time is not what we think it is? What if our entire perception of past, present, and future is an illusion, crafted by the mind to bring order to chaos? Physicists and philosophers alike have struggled to define time. It appears to flow, yet we have never seen time itself, only its effects. Clocks tick, seasons change, we grow older. But are these signs of time passing, or just transformations in matter and energy? Einstein shattered the classical notion of time with his theory of relativity. According to him, time is not a constant flow, but is woven into the very fabric of space. It can stretch and compress depending on gravity and speed. Time is relative, not universal. On a speeding spacecraft, time slows down compared to Earth. Near a black hole, time nearly halts. Imagine standing at the event horizon, where time moves so slowly compared to the rest of the universe that billions of years could pass outside in mere moments. This isn't science fiction. It's confirmed by atomic clocks flown in aircraft and by GPS satellites that need constant correction for relativistic time shifts. But the implications go even deeper. In Einstein's block universe concept, past, present, and future all coexist. Time doesn't move like a river. Instead, all events exist simultaneously. We are simply experiencing one slice of the block at a time. Think of a DVD. The entire movie already exists, yet we play it second by second. To us, the story unfolds. But from the DVD's point of view, it all already happened and always will. Could our universe be the same? This leads us to the idea of temporal illusion. Neuroscience tells us that our perception of now is a mental construction. Our brains stitch together moments to create a smooth sense of time. But in reality, events may be disjointed or even simultaneous. Could this mean free will is an illusion too? If the future already exists, are we simply following a predetermined script? Some physicists say yes. Quantum theory suggests all possible futures exist until one is observed, but even this doesn't fully break the illusion of choice. If everything is governed by probability and observation, then perhaps even choice is a consequence of deeper physical laws. However, other models challenge this deterministic view. The growing block universe proposes that only the past and present are real, while the future is constantly being written. In this view, time is like a tree, growing ever upward, branching with possibility. In yet another model, presentism, only the current moment exists. The past is gone, the future unwritten. It's the most intuitive idea of time, yet the least supported by physics. So where does that leave us? At infinity beyond, we ask, does it even matter if time is real? Or is the true mystery how time shapes consciousness its foes? We measure our lives in years, hours, seconds, but time as we feel it is deeply personal. 1 hour of joy can vanish in an instant. A single minute of pain can stretch into eternity. So maybe the real question isn't what time is, but how it feels, and how it ends. Entropy tells us that the universe is moving toward disorder. Over trillions of years, stars will die, galaxies will fade, and time itself may cease to have meaning in a cold, dark cosmos. But maybe that end is not the end. Perhaps, as we discussed before, the universe cycles. Perhaps time, too, is cyclical, a never-ending wheel of creation and destruction. Or perhaps time, as we know it, is just the blink of an eye in a reality far grander than we can comprehend. Whatever the truth, one thing is certain. The mystery of time is not just a problem for scientists. It is a riddle for anyone who has ever wondered where they came from or where they're going. And we will keep asking, because at infinity beyond, the journey never stops. Roughly 4 billion years ago, a moment of celestial chaos reshaped not just the moon, but the entire inner solar system. This period, known as the lunar cataclysm, or late heavy bombardment, saw a dramatic spike in asteroid impacts, triggered by a cosmic shift in the orbits of the gas giants, Jupiter and Saturn. Their gravitational dance disrupted the Kuiper Belt, flinging countless asteroids inward toward the rocky planets, Mercury, Venus, Earth, and the Moon. The Moon, still relatively young and orbiting just 86,000 miles from Earth, about a third of its current distance, was in the direct line of fire. Lacking an atmosphere to shield it, the lunar surface was battered relentlessly. Thousands of asteroids smashed into it, forming craters from half a mile to hundreds of miles wide. Some impacts were so intense they melted the crust, flooding massive basins with lava that cooled into the dark Maria we see today. It's a celestial canvas painted in fire and stone, but Earth did not escape unscathed. Though our planet has plate tectonics, erosion, and a recycling surface that wipes away ancient scars, scientists believe it suffered impacts as severe, if not worse, than those on the Moon. These collisions could have vaporized oceans, superheated the atmosphere, and sterilized entire regions. Life, if it had already taken root, would have faced extinction repeatedly. It was a time of cosmic violence that would shape the geological and biological history of our world. Some of the largest lunar craters, like the Imbrium Basin, span over 700 miles. These aren't mere dents in the Moon. They are records of titanic violence that released more energy than all nuclear weapons ever created. And while the Moon preserved these scars, Earth's surface quietly buried its own. Yet thanks to lunar geology, we can reconstruct what likely happened here on Earth during that same epoch. To better understand this shared history, scientists have studied lunar meteorites, pieces of the Moon knocked loose by impacts and eventually falling to Earth. These rare rocks, only about 30 have been discovered, tell a consistent story. A dramatic increase in impact events between 3.9 and 4.0 billion years ago. This bombardment likely struck both Earth and the Moon, seeding the inner solar system with craters, lava flows, and cataclysmic environmental change. Some of the ejecta from the Moon was so forcefully launched into space that it entered Earth's gravity and landed here. These are not just rocks, they are time machines. They contain geochemical clues older than any terrestrial sample. Ironically, the Moon, barren and lifeless, holds one of the most intact archives of Earth's earliest history. This realization led to an even more astonishing possibility. Could Earth rocks have landed on the Moon as well? After all, the impacts on Earth were often even larger than those on the Moon. The asteroid that likely caused the extinction of the dinosaurs, which struck Mexico's Yucatan Peninsula, was around 6 miles across. But some impacts during the lunar cataclysm were significantly bigger. One such event could have launched terrestrial material beyond Earth's atmosphere, fragments of our planet's early crust, possibly even bearing traces of early biology. These fragments would have arced through space and landed on the Moon, where they would be preserved indefinitely in the vacuum, frozen in time. Astrobiologist Guillermo Gonzalez estimates that more than 1,000 pounds of Earth rock could be scattered across every square mile of the lunar surface. And unlike Earth, where erosion, water, and volcanoes destroy ancient records, the Moon is geologically inactive. Once buried beneath layers of regolith, those fragments remain untouched, like fossils in a cosmic museum. If even a handful of those rocks contain signs of life, amino acids, simple cells, or organic molecules, they could revolutionize our understanding of Earth's biological origins. For now, none have been found, but future lunar missions may be able to retrieve and analyze these extraterrestrial Earth rocks. While science fiction often imagines the Moon as a dead, irrelevant world, it is anything but. Its surface has acted as a cosmic recording device, silently documenting the story of Earth's youth and the early solar system. Without it, we might never be able to piece together the events that led to life's emergence on our planet. The Moon's proximity during this chaotic era served another critical role. It absorbed many of the asteroid impacts that might otherwise have struck Earth. In a very real sense, the Moon became Earth's cosmic shield, taking blow after blow so that our fragile biosphere might someday flourish. Today, when we look up at the Moon and see its cratered face, we are not just seeing scars, we are seeing survival. Each mark is a reminder that Earth once danced through fire and death, and somehow emerged alive. The Moon's silent presence in our sky tells a story of destruction, yes, but also of protection, resilience, and the strange twists of cosmic luck that made life on Earth possible. The Moon has always been a silent guardian, stabilizing our axis, creating tides, slowing our rotation, nurturing the conditions for life. But what happens when that guardian slowly walks away? The truth is, the Moon is leaving us. Since it was born from the fiery collision that shaped our planet over 4.5 billion years ago, the Moon has been drifting away. Laser measurements from the retroreflectors left by Apollo astronauts have confirmed this. The Moon is receding at approximately 1.5 inches, 3.8 centimeters per year. At this rate, over the span of billions of years, its influence will continue to fade. Fast forward 500 million years from now. The Moon is now so far away that it can no longer fully eclipse the Sun. Total solar eclipses, once breathtaking marvels of cosmic geometry, will become impossible. Future generations, if any exist, will only witness annular eclipses, where the Moon covers the Sun's center but leaves a glowing ring of fire around the edges. And this is just the beginning of a greater unraveling. The further the Moon drifts, the weaker its gravitational grip on Earth becomes. One of the first and most immediate consequences will be on Earth's axial tilt. Currently fixed at about 23.5 degrees, this tilt is what gives us seasons. The Moon's gravitational tug stabilizes this angle, preventing it from wandering too far. Without the Moon's steadying hand, Earth will begin to wobble chaotically. This isn't a gentle sway, it's a violent swing. Earth's tilt could vary from degrees, no seasons, to 90-degree, extreme seasons, as it responds to the gravitational influences of the Sun, Jupiter, and Saturn. Such instability would bring climatic chaos. In one epoch, the Arctic might receive constant sunlight and melt into a swamp. In another, the equator might freeze solid under year-long winters. Entire ecosystems could collapse, unable to adapt to the wild shifts in sunlight, temperature, and rainfall. What's more, as the Moon recedes, its ability to generate strong tides will diminish. Already our oceans rise and fall with a rhythm set by the Moon. These tides oxygenate water, influence marine life, and shape coastal ecosystems. Without strong lunar tides, marine biodiversity could plummet. Coral reefs may bleach, fish migrations could stop, algae blooms might stagnate, even Earth's rotation will continue to slow. Right now, our planet spins once every 24 hours. But in the far future, this could extend to 30, 40, or even 60 hours per day. Long days would mean longer exposure to solar radiation, scorching half the globe, while the other half freezes in darkness. Temperature gradients would become extreme. Weather systems could break down. Sleep cycles, circadian rhythms, and biological timing, as we understand them, could be lost. Life would have to adapt or perish. And this isn't merely theoretical. Astronomers already observe other planets with chaotic axial tilts. Uranus, for example, lies nearly sideways, with its poles facing the Sun. Mars, without a large moon to stabilize it, also experiences massive axial shifts. It's one reason Mars has such unpredictable climate swings, and likely one reason why life there, if it ever existed, never took hold in a stable way. Back on Earth, the slow disappearance of the Moon would even affect the shape of our planet. Right now, the Moon's gravity pulls up a tidal bulge, not just in oceans, but in the crust itself. As this influence weakens, Earth's equatorial bulge may lessen, subtly reshaping ocean currents and wind patterns. And with no stabilizing tides to slow Earth's spin further, another equilibrium might eventually be reached: tidal locking. In the extreme far future, billions of years from now, Earth could become tidally locked to the Moon just as the Moon is to us. That means Earth would always show the same face to the Moon and the Moon to us. But even that state is temporary, because long before that happens, our Sun will intervene. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing Mercury, Venus, and possibly Earth and the Moon. Our twin celestial partners, who have orbited each other in a delicate gravitational embrace, will die together, swallowed by solar fire. Their long journey, shaped by cosmic collisions, tidal dances, and evolutionary miracles will end not with an explosion, but with an incineration. And yet, perhaps that's the most poetic finale possible. Earth and Moon, born of the same celestial trauma, forged in a single moment of cosmic violence, will vanish as one together. Still, long before that distant doom, the Moon's retreat will have rewritten the story of life on Earth. Our comfortable, stable planet will no longer be a haven for complex life. The Moon's departure will unravel the system it helped build. We may think of the Moon as passive, silent, constant, but in truth, it is a dynamic architect of our survival. And as it fades, so may we. The 1969 laser reflector experiment confirmed an astonishing truth. The Moon is steadily drifting away from Earth. Though moving at a seemingly insignificant rate of 1.5 inches, about 3.8 centimeters per year, this retreat has dramatic long-term consequences. Scientists in the 1990s turned to powerful supercomputers to simulate what happened during the colossal impact that gave birth to the Moon. What they found reshaped our understanding of Earth's early dynamics. Their models revealed that the collision between Theia and Earth wasn't a head-on crash, but rather a glancing blow. This tangential impact imparted tremendous angular momentum to Earth, sending it spinning on its axis far faster than it does today. In the chaotic aftermath of the impact, Earth rotated once every 6 hours, 4 times faster than its current 24-hour day. Meanwhile, the newly formed Moon, still glowing red-hot from the trauma of its birth, orbited the Earth once every 20 days. At this stage, the Moon was 15 times closer to Earth than it is now, and its gravitational pull was immense. In fact, the gravitational tug of the early Moon on our planet was so intense that it deformed the Earth's surface. A massive tidal bulge, an actual uplift of rock and water, followed the Moon in its orbit, slightly offset due to Earth's faster spin. This bulge created a continuous drag on Earth's rotation, while simultaneously tugging the Moon forward in its orbit. This interplay of forces led to a phenomenon known as tidal acceleration. As the Moon's gravity pulled on Earth's bulge, it gained orbital energy and slowly spiraled away. Simultaneously, Earth's own rotation slowed. Over time, the day lengthened from 6 hours to the 24 hours we experience today. And while this change took hundreds of millions of years, its effects were pivotal to shaping a stable, habitable planet. The Moon's close proximity, however, came with a cost. It found itself in the firing line of a brutal, celestial bombardment. Approximately 4 billion years ago, during a period known as the Late Heavy Bombardment, or the Lunar Cataclysm, a gravitational disturbance between Jupiter and Saturn altered the orbits of countless asteroids in the outer solar system. Many were flung toward the inner planets, including Earth and its newly formed satellite. The Moon, then only about 86,000 miles away from Earth, bore the brunt of this onslaught. Thousands upon thousands of meteorites pounded its surface, destroying approximately 80% of its crust. Immense craters formed, some stretching hundreds of miles across. Molten rock erupted from fissures caused by impacts, flooding craters and cooling into vast basalt plains, which we now call Maria, Latin for seas. One such sea, the Sea of Tranquility, would become the landing site for Apollo 11 nearly 4 billion years later. From Earth's surface today, the pattern of these dark basalt plains creates the illusion of a face, the famous man in the moon. But those features are scars from a savage past, a violent record of the solar system's chaotic youth. Astrophysicists like David Kring have studied these craters in extraordinary detail. Some number over 300,000, ranging in size from half a mile to more than 500 miles in diameter. The largest visible from Earth is the Imbrium Basin, which stretches nearly 700 miles across. These impact sites are far more than cosmic curiosities. They're time capsules from a forgotten age. Occasionally, the impacts were so powerful that debris ejected from the moon's surface didn't fall back. It was hurled into space. Some of this lunar material was drawn into Earth's gravity well and fell to our planet as lunar meteorites. Only about 30 such meteorites have ever been found, but they are invaluable. Embedded within them is a geological record billions of years old, far older than any rock found on Earth, where erosion and plate tectonics have erased nearly all traces of our earliest history. The discovery of these meteorites sparked an intriguing question. If rocks from the moon could land on Earth, could the reverse be true? Could early Earth rocks, blasted into space during the cataclysm, have landed on the moon? And more tantalizingly, could those rocks contain chemical signatures of early life? Launching anything from Earth into space requires immense energy. NASA's space shuttle, for instance, used over 15 million horsepower to break free of Earth's gravity. By comparison, the lunar module needed just 6,300 horsepower to escape the moon's weaker gravity. The difference is immense. But during the lunar cataclysm, Earth's surface was pounded by meteorites and asteroids of extraordinary size, some even larger than the impactor that wiped out the dinosaurs. These impacts punched holes in Earth's atmosphere, allowing fragments of Earth's crust to escape into space. Some of that material, by sheer gravitational alignment, could have landed on the moon, preserving early traces of life in the vacuum of space, protected from erosion, weather, and geological recycling. Astrobiologist Guillermo Gonzalez estimates that over 1,000 pounds of terrestrial rock could be spread over every square mile of the moon's surface. If even a few of those rocks contain organic molecules or fossilized microbial life, they could help answer one of humanity's oldest questions. How did life begin on Earth? So far, no confirmed Earth rocks have been identified on the moon, but future lunar missions may one day uncover these time-traveling messengers, offering a glimpse into the ancient story of our planet. In a strange twist of fate, the moon, a lifeless world, may hold the most pristine record of Earth's origin story. Though the moon has long inspired myths and romance, it may also play a far darker role, one that science is only beginning to confront. While its glow bathes Earth in soft silver light, its gravity may stir violent forces far beneath our feet. Some scientists believe that the moon's gravitational pull, especially when combined with the sun's, can trigger volcanic eruptions and earthquakes, tilting the balance at tectonic fault lines. This idea, once dismissed as folklore, is gaining cautious attention as data mounts. One of the strongest proponents of this theory is Jim Birkeland, a former geologist with Santa Clara County, California. In 1989, Birkeland caused a stir when he predicted a significant earthquake would hit the San Francisco Bay Area just days before the devastating Loma Prieta quake, which occurred during the World Series. It measured 6.9 on the Richter scale, killed 63 people, and caused over $6 billion in damage. Birkeland's predictions, controversial and often criticized, were based in part on the position of the moon during perigee, its closest point to Earth, and on tidal stress patterns. He believed that when the moon and sun aligned, during full or new moons, their combined gravity increased stress on Earth's crust, acting as a final trigger for earthquakes already primed to rupture. While mainstream geologists remained skeptical, Birkeland persisted. He tracked lunar cycles, animal behavior, tide charts, and even lost pet reports, forming a kind of multidimensional forecasting system. Though not scientifically orthodox, some of his predictions appeared eerily accurate. Critics called him lucky. Supporters called him prophetic. But Birkeland wasn't alone. In the 1990s, volcanologists Steve and Donna O'Meara began to study correlations between lunar phases and volcanic eruptions. On an expedition to Arenal volcano in Costa Rica, they noticed a pattern. Eruptions consistently peaked when the moon was directly overhead or beneath the volcano. They mapped the moon's position during multiple eruptions and found that it correlated with increased tidal stress beneath the surface. In fact, the Omeras claim to have predicted eruptions with up to 80% accuracy by simply tracking the moon. Skeptics remain, pointing out that Earth's crust is complex and that many factors, pressure, gas buildup, water infiltration, can cause an eruption. But the theory is compelling. The moon's pull doesn't cause eruptions or quakes by itself. It simply adds the final nudge, the last straw, to a system already on the brink. This idea becomes even more intriguing when applied to solar eclipses. During an eclipse, the moon, sun, and Earth align in perfect syzygy. The gravitational forces line up as well, creating an astronomical tug-of-war that may cause dramatic increases in tidal stress. Birkeland traveled to Peru to witness a solar eclipse and reported that locals anticipated an earthquake to follow. They were not disappointed. Within days, seismic activity was recorded in the region. Could it be that ancient cultures knew something we forgot? That the moon, in perfect alignment, becomes more than a mystical symbol. It becomes a geophysical trigger. The science behind this is subtle. Earth's crust isn't a single shell, but a mosaic of tectonic plates floating atop semi-molten rock. These plates constantly shift, driven by internal heat, gravity, and pressure. When one plate grinds against another, stress builds. Eventually, the stress becomes too great, and the crust slips, causing an earthquake. Now, imagine this system under the influence of additional gravitational stress. During perigee, the moon is about 30,000 miles closer to Earth than at apogee. This proximity increases its pull by about 20%. When perigee coincides with new or full moon phases, called a perigean spring tide, the combined stress on Earth's crust and oceans can be enormous. Add a solar eclipse into the mix, and you get a rare moment of maximum tidal force. For a fault line already under strain, this may be enough to trigger a rupture. In 2004, a massive 9.1 magnitude earthquake struck off the coast of Indonesia, triggering a catastrophic tsunami that killed over 230,000 people. It occurred the day after a full moon. In 2005, just after a solar eclipse passed over Pakistan, a 7.6 magnitude earthquake devastated the Kashmir region, leaving 87,000 dead. While correlation does not equal causation, these events have sparked renewed interest in lunar influence. Some geologists have begun incorporating tidal data into their seismic models. Others remain cautious, wary of turning science into astrology. But even NASA has acknowledged that the moon plays a role in modulating tidal stress, particularly in shallow fault zones near the ocean. It's not an outright endorsement of lunar-triggered quakes, but it's not a denial either. If true, this means that the moon, even today, is not done shaping Earth. Its influence may have shifted from oceans and winds to something deeper and more destructive, an invisible hand pressing on the trigger of the planet's most violent forces. Yet even as the moon drifts farther away, its pull may remain powerful. And perhaps that's the most haunting truth of all. Something so distant and silent might still be dictating when and where our planet shakes. Picture Earth. 3 billion years ago. It is still a dangerous, dynamic world. A planet alive with volcanic eruptions, violent storms, and shifting continents. But slowly, quietly, a transformation is unfolding. At the heart of that change is a force both distant and familiar. The Moon. By this point in its retreat, the Moon orbits nearly 200,000 miles from Earth. Its tidal influence has decreased from its primeval power, but it's still strong enough to reshape coastlines, control ocean rhythms, and exert its invisible influence on the planet's spin. Over the previous billion years, the Moon's constant gravitational tug has slowed Earth's rotation dramatically, from 6 hours per day to something closer to 18 hours. But this change isn't just mechanical, it is climatic, atmospheric, and biological. The Earth's faster rotation had created extreme wind systems. When a planet spins quickly, it drags its atmosphere with it. The result? Perpetual hurricane-force winds roaring around the globe. These weren't storms that came and went, they were daily life. In this chaos, early life was confined to sheltered areas, deep oceans, rocks, and tiny tide pools. Atmospheric scientist Neil Commons compares the effect to modern hurricanes. When we get winds of 100 mph today, trees are uprooted, buildings are torn apart. But imagine a planet where that wind never stopped. This was Earth for hundreds of millions of years, but the moon began to change that. As the moon pulled on the Earth's oceans, raising tidal bulges, friction between the water and the land converted some of Earth's rotational energy into heat. That energy was lost to space, and the planet's spin began to slow. With a longer day came less atmospheric turbulence. Gradually, weather patterns settled into more predictable forms. This was no overnight miracle. It took eons. But eventually, the sky calmed. Winds dropped. Ocean currents stabilized. The atmosphere became a blanket instead of a battlefield. With this newfound atmospheric peace, the surface of Earth began to open up as a canvas for evolution. Larger, more fragile life forms, no longer at constant risk of being shredded by gale-force winds, emerged. Multicellular organisms began to flourish. Over time, these organisms would develop into algae, corals, plants, and eventually animals. And once again, the moon's influence was critical. The lengthening of Earth's day to 24 hours brought a new rhythm to the planet, a daily cycle of light and darkness, regular enough to shape biological systems. Plants evolved to open their leaves by day and close them by night. Animals became nocturnal or diurnal. Circadian rhythms, internal biological clocks, developed in response to the new day-night stability. This was no coincidence. Evolution thrives in rhythm. Predictable cycles allow species to specialize, adapt, and plan for change. Without the moon's slow-down effect, days might still last only 8 or 10 hours. There might be no time for rest, no time for photosynthesis, no time for sleep. Earth would be a place of continuous struggle, too harsh for complexity. What's more, the stabilization of wind and water cycles had a compounding effect. As weather grew more stable, erosion patterns changed. River valleys began to form. Lakes lasted longer. Rainfall followed more predictable paths. Ecosystems became structured, allowing food webs and biodiversity to flourish. In this relatively calm environment, evolution kicked into high gear. Over hundreds of millions of years, the first fish appeared, then amphibians, reptiles, mammals, and birds. Entire forests grew, nourished by regular sunlight and manageable climates. And still, above it all, the moon watched, slowly receding into the sky, its job not yet finished. Even today, the effect of this long deceleration remains. Earth's 24-hour rotation is not permanent. It's still slowing, imperceptibly, second by second. In the distant future, days may grow even longer. But it is the moon that set this process in motion, giving Earth the time and balance it needed to grow intelligent life. To illustrate this interaction, scientists often use a globe and lens demonstration. Imagine Earth as a spinning globe, and the moon as a heavy lens in orbit. The moon raises tides on Earth, bulges of water aligned not perfectly underneath the moon but slightly ahead, due to Earth's faster spin. These bulges act like brakes, pulling backward on Earth's rotation while flinging the moon outward. This gravitational tug-of-war creates a tidal drag, slowly draining Earth's rotational energy and flinging the moon ever farther away. The more the Earth slows, the less dramatic the bulges, and the longer it takes for the moon to continue drifting. It's a cosmic feedback loop, gentle yet relentless. This system also affects the Earth's shape. Without the moon's pull, Earth would be slightly more spherical. But with tides pulling unevenly on the oceans and crust, our planet has developed an equatorial bulge. These distortions influence tectonic stress, ocean currents, and even the length of a year. It's remarkable to think that something as distant and silent as the moon could control so many aspects of life. And yet the evidence is overwhelming. From the calming of winds to the creation of night and day, from the origin of tides to the rhythm of sleep, the moon has shaped us, not metaphorically, but literally. Remove the moon, and you remove the seasons, the tides, the 24-hour day. You remove the early shelter that allowed life to begin, and the late-stage climate that allowed it to flourish. You remove the predictable cycles that trained our brains to sleep, eat, move, and love. So the next time you glance up at the moon and wonder if it matters, remember this: everything about you, your breath, your heartbeat, your very existence, is in rhythm with something that once tore through the sky in a wave of fire and was reborn as Earth's eternal companion. Imagine a world ravaged by hurricane-force winds, where the atmosphere howls relentlessly, and where the day lasts a mere 6 hours. Temperatures swing violently, shifting from scorching heat to a bitter, icy cold with startling frequency. This nightmarish vision isn't a scene from a dystopian sci-fi movie. It's what our planet could have become had the moon never existed. Hovering silently above us at nearly 250,000 miles, the moon, a massive sphere of rock and dust measuring more than 2,100 miles in diameter, has quietly shaped our world in profound ways. Despite being lifeless, barren, and inhospitable, with surface temperatures soaring to 250 degrees and plummeting to 380 degrees, it is the second brightest object in the night sky. Its gravity is 1/6 that of Earth, and its dry, crater-scarred terrain features mountains soaring over 16,000 feet high. No liquid water has ever been found on its surface. Yet, in human culture, the moon has always held a sense of mystery and allure, symbolizing romance, transformation, and the supernatural. Throughout the solar system, Earth is not unique in having a moon. In fact, over 135 moons orbit the planets around us, with Saturn boasting the most, currently recorded at 46. But our own moon stands out in both size and impact. Besides Earth, there are at least 10 other mysterious objects orbiting our planet. 5 are temporary asteroids caught in Earth's gravitational embrace, and 4 are likely remnants from past space missions, possibly parts of the Apollo 12 rocket. The 10th and largest, of course, is our moon, which has orbited Earth since long before humans existed. Despite its long-standing presence in our skies, we knew very little about the moon's origins until the 20th century. For centuries, its creation remained one of astronomy's greatest mysteries. Several theories emerged to explain its existence. One suggested that the moon might simply be a wandering asteroid or planet that had been captured by Earth's gravitational pull. Another theory proposed that Earth and moon formed together, side by side. A more explosive theory emerged. The moon was born out of a colossal collision between a young Earth and another planetary body. It wasn't until the Apollo missions that real clues began to emerge. Between 1969 and 1972, 12 astronauts landed on the moon as part of 6 separate missions. They brought back not just unforgettable footage and national pride, but actual lunar rock samples, precious relics holding secrets from the dawn of the solar system. The rocks revealed a striking similarity to Earth's own geological materials, yet they were noticeably lacking in iron content. This subtle but significant difference hinted at an explosive origin. The moon was likely formed by a massive impact. To explore this idea, we travel back more than 4.5 billion years, to a chaotic time when the solar system was young and volatile. During this era, the inner solar system contained nearly twice as many planetary bodies as it does today. One of them was a Mars-sized planet known as Theia, named after the mythical Greek goddess who mothered the moon. Theia's trajectory gradually aligned with that of the young Earth, setting the stage for an apocalyptic collision. As Theia approached, it would have grown in the sky, first appearing as a bright star, then a looming planet, and finally a terrifying presence that filled the entire horizon. The impending impact would unleash forces unimaginable to the human mind. Theia, 4,000 miles in diameter and traveling at 25,000 miles per hour, 20 times faster than a supersonic jet, would slam into Earth with the force of billions of megaton bombs. This wasn't a direct hit. It was a glancing blow, a cataclysmic brush that ripped away massive chunks of Earth's crust, ejecting iron-poor surface rock into space. Much of this material fell back to Earth, but some of it escaped and just far enough to become trapped in orbit. What followed was a process known as accretion. Dust and rock fragments collided, fused, and gradually gathered into clumps. These clumps combined under mutual gravitational attraction until they formed a red-hot ball of molten rock. Within just 100 years, this ball cooled and solidified, becoming the Moon. At the time of its formation, the Moon was only 17,000 miles away, appearing 15 times larger in the sky than it does today. Its violent birth sent it spinning outward in a gradual journey that would last billions of years. Today, it continues to drift away at a rate of about 1.5 inches per year, a fact confirmed by astronauts in 1969, who placed an 18-inch reflective plate on the lunar surface, allowing scientists to precisely measure the distance using lasers. As the Moon continued its slow retreat from Earth, reaching distances of around 200,000 miles some 3 billion years ago, its pull on our oceans remained profound. Though the tidal effect was gradually weakening with distance, it still held enough influence to fundamentally reshape the chemistry of Earth's seas, and perhaps spark the very beginning of life itself. At this point in history, Earth was already rich in water. Oceans covered much of the planet's surface, and the ingredients for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, were present. But it wasn't just a matter of ingredients. These elements needed energy, turbulence, and time to combine into complex molecules. And it was the Moon's tidal forces that provided this essential turbulence, acting as a planetary spoon stirring the primordial soup. Each time the Moon passed overhead, it pulled on Earth's oceans, raising tides that were still hundreds, sometimes thousands of feet high. These tides were not slow or gentle. They moved like massive walls of water, sweeping inland for miles, carrying minerals, organic material, and heat with them. When they retreated, they dragged debris back to sea, mixing everything into a chaotic but potent chemical cocktail. This continuous churning of the oceans didn't just influence the sea, it sculpted the land. Tides scraped coastlines, carved estuaries, and created tidal pools, isolated shallow bodies of water that evaporated and refilled day after day, cycle after cycle. Many scientists believe these pools may have been the ideal environment for the origin of life. As the pools dried, compounds became concentrated. When they refilled, they mixed again, creating new chemical combinations. Through these repetitive cycles, simple organic molecules could form, grow, and most crucially, replicate. Some researchers believe that early strands of RNA or proto-DNA may have first formed under such conditions, and the rising and falling of water levels, caused by the Moon, may have facilitated a key event in life's emergence, the splitting and copying of early genetic material. Like the opening and closing of a zipper, fluctuating salt concentrations and drying cycles could have forced strands to unzip and reassemble, a primitive form of replication, the fundamental property of life. In this way, the moon wasn't just a stabilizer of Earth's tilt or a protector from asteroids. It may have actively engineered the chemistry of life by driving the physical conditions necessary for molecular evolution. Without these extreme tides, stirred by a nearby moon, Earth's oceans might have remained chemically stagnant, and life might have taken far longer, or never emerged at all. Moreover, those early tides did more than nurture biology. They helped calm the violently spinning Earth. As we've explored before, Earth's rapid rotation after the moon-forming impact caused atmospheric instability. Days lasted just 6 hours, and the winds were unimaginable, more like permanent global hurricanes than passing storms. Atmospheric scientist Neil Commons notes that wind speed on early Earth was tied directly to rotation speed. With the planet spinning 4 times faster than it does today, wind systems circled the globe at terrifying velocities. Today, hurricane winds reach 100 to 150 miles per hour and last a few days. Imagine that same intensity as a daily condition, never ceasing. Nothing large or complex could evolve in that chaos. But the moon's gravity slowly tamed this tempest. Through the constant drag of tides, it exerted torque on Earth's spinning body. Over billions of years, this drag stretched Earth's day from 6 hours to 12, then 18, and finally to the 24-hour cycle we know today. As the spin slowed, wind systems calmed. Climate patterns stabilized. The atmosphere, once turbulent and violent, became a more hospitable envelope around the planet. With this new stability, primitive life was no longer just surviving. It had a chance to diversify, specialize, and evolve. This wasn't just about temperature and storms. Climate regulation affected light exposure, seasonal rhythms, and ecological niches. It allowed photosynthetic organisms to flourish, oxygenating the atmosphere. It enabled food chains to develop and made possible the eventual evolution of complex multicellular organisms. So we begin to see a full picture emerge. The moon is not just a passive companion in the night sky. It is an active force in Earth's biological history. It set the stage, created the conditions, and orchestrated the tempo of evolution itself. By the time we reach 2.5 billion years ago, Earth is already beginning to look familiar. Oxygen-producing bacteria are transforming the atmosphere. Life is no longer confined to tide pools. The continents are shifting, volcanoes are active, and deep in the oceans, new ecosystems are thriving. All of it unfolding under the steady, ever-receding gaze of the moon. And still, its work is not yet done. While its tidal grip has loosened, its influence persists, not only in the rhythms of the sea, but in the behavior of certain animals, the synchronization of reproductive cycles, and even, perhaps, the hidden pulses of human emotion. But before we dive into these mysteries, we must first finish understanding what the moon truly gave us, a world that could breathe, evolve, and survive itself. Throughout this journey, across billions of years and unimaginable cosmic events, we've followed the moon from its fiery birth to its slow retreat across the heavens. It began as the result of a planet-shattering collision, and it ends as one of the most crucial players in Earth's habitability. And now, as we stand on this tiny blue world and look up, we must ask, would we even be here without it? The answer, in all likelihood, is no. The moon has been far more than a beautiful ornament in the night sky. It is not just a light to write poems about, nor merely a trigger for tides. It is a cosmic engineer, a celestial force that shaped Earth's climate, spin, oceans, atmosphere, and biological rhythm. Let's trace just a few of its indispensable gifts. First, the moon stabilized Earth's axial tilt. Without this, the planet would wobble wildly, swinging between extreme tilts. This would cause catastrophic climate shifts, ice ages at the equator, deserts at the poles, and violent, unpredictable seasons. Stable axial tilt, gifted by the moon's gravity, gave Earth a predictable climate where life could flourish. Second, the moon slowed Earth's rotation. From a frenetic 6-hour day to our current 24-hour cycle, the moon created a world where days and nights allow for rest, energy cycles, temperature regulation, and circadian rhythms. Life evolved in sync with this rhythm, from the tiniest microbes to the largest mammals. Third, the moon gave us tides. The rising and falling of oceans mix nutrients, oxygenate water, drive ecosystems, and enable migratory patterns. Long before complex life, the moon's tides stirred the primordial soup that may have given birth to DNA itself. Without tides, perhaps no replication. Without replication, no life. Fourth, the moon acted as a shield. During the late heavy bombardment, Earth was under siege by asteroids. The moon absorbed countless impacts that may have otherwise obliterated our planet's surface and sterilized early life. The very scars we see on its face are sacrifices made on our behalf. Fifth, the moon enabled eclipses, calendars, and the earliest measurement of time. It became a cultural compass, a spiritual mirror, a teacher of cycles. Our ancestors aligned monuments to its phases. Farmers planted by its light. Poets found metaphors in its changing face. Sixth, the moon possibly continues to influence natural disasters. While still debated, some evidence suggests that lunar gravitational pull contributes to tectonic stress. Earthquakes, volcanic eruptions, and even tsunamis may have the moon's fingerprints in their timing. And then there is the mystery of the human connection. The lunar cycle's subtle influence on behavior, biology, and sleep. From werewolf legends to modern police reports, we continue to sense the moon's emotional gravity, even if we cannot fully explain it. But perhaps the moon's most astonishing role is this: it may be unique in the universe. Despite the vast number of planets we've discovered, over 5,000 confirmed exoplanets, very few appear to have large moons. Earth's moon is unusually massive relative to the size of its host planet. It's about 1/4 the diameter of Earth. For comparison, Mars's 2 moons are tiny potato-shaped rocks. Jupiter and Saturn have dozens of moons, but they are proportionally much smaller compared to their massive parent planets. This size matters. The moon's gravitational influence is directly tied to its mass and distance. Without something so large and perfectly placed, Earth might have become a world of chaos. Too unstable, too violent, too hostile for life as we know it. Which raises a humbling thought. What if we're rare? What if our moon is the cosmic exception, not the rule? And what if intelligent life, like us, requires not just a habitable planet, but a large moon to stabilize and nurture it? If that's true, then Earth is not just lucky. It is extraordinary. It also means that as we search the stars for other life-bearing worlds, we must start asking, do they have a moon? Not just water, not just temperature, not just oxygen, but a stabilizing companion that can shepherd a planet toward balance. And yet, despite all this, the moon is moving away. One day, it will be too distant to sustain eclipses, too weak to stabilize our tilt, and too far to stir the oceans. And finally, in a fiery cosmic finale, it will be consumed along with Earth by the dying sun. But that future is distant. For now, the moon is still with us. It still guides the tides, measures our months, lights our nights, and keeps the planet from tipping into chaos. And when we gaze up at it, whether on a clear night or during an eclipse, we're not just seeing a rock. We're seeing the reason we're alive. We're seeing our ancient protector, our celestial twin, our silent partner in life. And perhaps, knowing all this, we'll look at the moon a little differently, not as a cold, distant orb, but as the quiet force that helped write every chapter of Earth's story, including our own. As Earth settled into its 24-hour rhythm and complex life blossomed across its surface, the moon continued its quiet retreat, always present, always watching. Over billions of years, it became more than a celestial object. It became a symbol, embedded in the minds, hearts, and stories of humankind. At 250,000 miles away, the moon now orbits our planet in a perfect cosmic balance, exerting a gravitational pull just strong enough to move oceans, but not strong enough to disturb tectonic plates. Its glow, soft, cold, and cyclical, has inspired myths, rituals, and even madness. Across every civilization and every age, the moon has been a mirror for human emotion. Long before telescopes or space travel, our ancestors looked up and saw patterns on its surface. Some imagined a man carrying a bundle of sticks. Others saw a rabbit pounding rice. Still others told of a goddess residing on the moon, or that the moon was the source of dreams and death. It was the keeper of secrets, the ruler of tides, and a harbinger of transformation. But the moon's influence isn't just cultural. It may still shape human biology and behavior in ways science is only beginning to understand. One of the most ancient and persistent beliefs is that the full moon triggers madness or heightened emotions. The term lunacy itself derives from luna, the Latin word for moon. Stories of werewolves, full moon transformations, and mystical energies have echoed across centuries. But is there any truth behind the myth? Modern science has tried to answer that. In 1976, a study published in the American Journal of Psychiatry analyzed over 34,000 crimes and found a noticeable increase in violent incidents during the full moon. A year later, another study of 18,000 psychiatric patients revealed higher admission rates during the new and full moon phases. However, subsequent research has been less conclusive. Some modern studies find no statistically significant correlation between lunar phases and crime, hospital visits, or psychiatric episodes. Others suggest small effects, but nothing consistent or universal. Still, many people, including paramedics, police officers, and ER doctors, insist that the full moon does change things. They feel it. They see it. Is it confirmation bias? Or is there something more subtle at work? Biologists have observed that some animals are strongly attuned to the lunar cycle. Coral reefs, for example, often spawn synchronously during full moons. Certain fish time their reproductive cycles to the moon's light. Birds migrate in patterns that align with lunar brightness. Nocturnal predators hunt more effectively under a full moon, and prey animals become more cautious. This makes sense. Moonlight can alter visibility, navigation, and even hormonal rhythms. In some insects and small mammals, the moon affects melatonin production, influencing sleep cycles and activity levels. It's possible that early humans, too, were more active under bright moonlight, and that some of those behaviors are still subtly coded into our neurology. The idea that humans are immune to lunar influence might be a modern delusion. After all, we are 60% water, and if the moon can move entire oceans, perhaps it can stir something small and hidden within us too. But beyond biology, the moon has long been a marker of time. The lunar calendar, based on its 29.5-day orbit, was one of humanity's earliest systems of measurement. Ancient cultures, from the Babylonians to the Chinese to the Maya, used lunar cycles to determine planting, harvests, and sacred days. Even today, major holidays like Ramadan, Passover, Easter, and the Mid-Autumn Festival are timed by the moon. The moon's slow transformation across the sky, from new to crescent to full and back again, offered a perfect visual metaphor for change, death, and renewal. It became a spiritual compass, a cosmic metronome, a source of comfort in its predictability. And the moon isn't just visible, it's interactive. In 1969, when Apollo 11 astronauts left behind a reflective plate on its surface. It became a tool for laser measurement. From Earth, scientists have used this reflector to precisely track the moon's retreat, 1.5 inches per year. It's not just a poetic distance, it's a scientific fact. This ongoing dance, Earth's slowing spin and the moon's outward spiral, continues to shape the Earth in subtle but significant ways. Even today, the moon may influence tectonic stress, subtly nudging fault lines closer to breaking point. Some geologists, like Jim Birkeland, believe that lunar alignments, especially during perigee, the closest point in the moon's orbit, may trigger earthquakes. While this remains controversial, it is a theory gaining renewed interest. There are even volcanologists who track the moon's position to predict eruptions. They argue that the moon's gravitational tug can cause molten rock under pressure to shift just enough to break the crust at volcanoes' weakest points. In certain locations, like Costa Rica's Arenal volcano, eruptions have occurred with eerie precision under lunar influence. Whether in myth or in measurable data, the moon's legacy is undeniable. It is our nightlight, our calendar, our myth maker, and perhaps our stabilizer still. Looking ahead, the moon's power continues to wane. It drifts farther each year, and 500 million years from now, it will be too far away to create total solar eclipses. And eventually, its stabilizing grip on Earth's tilt may weaken, leading to climatic chaos. But for now, it remains silent, steady, silver bright, pulling on our oceans, our calendars, and perhaps even our hearts. As Earth continued to spin rapidly with 6-hour days, and the moon gradually drifted farther away, a silent but profound transformation was unfolding. The collision that created the moon not only slowed Earth's rotation over time, but also permanently altered the planet's orientation in space. That change, subtle at first, was monumental in its consequences. It tilted Earth's axis. Because of this tilt, Earth's axis now leans at approximately 23.5 degrees, and it is this slant that gives us our seasons. Without that tilt, Earth would spin upright, like the planet Mercury, and every region would receive 12 hours of daylight and 12 hours of darkness. No spring, no summer, no autumn, no winter. The poles would remain trapped in an eternal whoosh, while the equator would roast endlessly under the unrelenting heat of the sun. Life, as we know it, diverse and seasonal and dynamic, might never have evolved. But even more critically, the moon acts as a stabilizer. Astrobiologist Lynn Rothschild explains that without the moon, Earth's axis would not remain fixed. Our world would experience what scientists call chaotic obliquity, wild fluctuations in axial tilt, ranging from 0 to 90 degrees. These erratic swings would redistribute sunlight drastically across the globe, plunging tropical zones into icy winters and pushing polar regions into scorching summers. This kind of chaos would devastate ecosystems, trigger mass extinctions, and prevent the long-term stability needed for complex life to flourish. It's the moon's gravitational pull functioning like a global gyroscope that dampens these swings. Thanks to this celestial stabilizer, Earth's climate patterns, while not always gentle, have remained relatively predictable over geological timescales. To understand how critical this is, consider Mars. The red planet also has seasons, but they are wildly inconsistent. Mars has 2 tiny moons, Phobos and Deimos, which are too small to stabilize its axis. As a result, its tilt has shifted dramatically over millions of years, swinging between 15 and 45 degrees or more. Scientists believe this instability is a key reason why Mars, though it may have once had liquid water and perhaps primitive life, failed to sustain a biosphere like Earth's. So, while Earth spins on its tilted axis, the moon keeps that tilt from tumbling. But the moon's influence doesn't end there. Its gravitational dance with Earth also plays a pivotal role in one of the most life-sustaining processes on our planet: the tides. Billions of years ago, when the moon was still closer, its tidal pull was much stronger. Tides then were nothing like the gentle rises and falls we experience today. Instead, they were colossal, towering thousands of feet high, capable of surging inland for hundreds of miles. They roared across the planet with the power of a liquid mountain range, dragging surface minerals and sediments back into the sea. Astronomer Neil Commons studies how these early tides may have catalyzed the chemical complexity necessary for life. The immense mixing action churned nutrients and minerals into what scientists call the primordial soup, a rich, volatile ocean of chemical reactions. Molecules were bound together and pulled apart again and again until eventually the first building blocks of life, proteins, amino acids, RNA, began to emerge. Some researchers even believe that the moon's gravitational influence might have helped spark the earliest replication of DNA. As tides surged and receded, they could have altered chemical concentrations on ancient shorelines, encouraging the separation and rejoining of primitive strands of genetic material. Without these fluctuations, it's possible that life on Earth would have remained simple, or never begun at all. And these tides had another hidden benefit. They helped calm Earth's atmosphere. In the chaotic early days, Earth's faster rotation and short days generated constant hurricane-force winds. With a 6-hour day, wind systems circled the globe with terrifying speed and violence. Today, hurricanes may last a few days and travel a few hundred miles. Back then, hurricane-like conditions would have been perpetual. These winds made Earth a hostile, unlivable world. But the friction caused by the moon's tidal forces gradually slowed Earth's rotation. As days lengthened from 6 to 8, then 12, and eventually to 24 hours, the winds also lost strength. The atmosphere began to settle, and weather systems became more temperate. The moon's gravity not only gave Earth seasons and tides, it pacified the climate, allowing life to evolve beyond single-celled organisms. In a sense, the moon didn't just accompany Earth through the ages, it parented it. It helped craft a world that could nurture forests, oceans, animals, civilizations, and eventually, consciousness itself. Our relatively calm Earth, with predictable climates, stable seasons, and manageable weather, owes this gift not just to its position in the habitable zone of the Sun, but to the steadfast presence of its moon, a cosmic partner that may have made life not only possible, but sustainable.